Today we want to talk about parametric equations. This is another way that we can describe a curve in two-dimensional space. What we're trying to do is describe one-dimensional curves in two-dimensional space. So what we spend a lot of our time doing in math class is just describing stuff and introducing you to the language that we use in describing that stuff. So parametric equations. We are describing a one-dimensional curve in two-dimensional space. Our abbreviation for two-dimensional space is R2. We make a double R, we make a real number, and then we put a superscript of 2, and we just pronounce that R2. So that's how to pronounce that. Kind of appropriate given my outfit today. So we pronounce that as R2, and we're talking about two-dimensional space. When we talk about three-dimensional space, we'll call it R3. We already talked about one-dimensional space where we just say R, the number line. So it's just two real number lines slapped together at the 0 point at 90 degrees. That makes R2. We already have methods for describing curves in two-dimensional space. But the methods that we have rely on a relationship between the variables. So our methods so far for describing these curves rely on a relationship between the variables. Our methods so far for describing curves rely on a relationship between the variables. We express these as a relationship between the variables. The first thing that we try is we use a function. The reason that we start off with functions is because functions is easiest. So one of the methods that we use is we make a function. Specifically, we write y as a function of x. The restriction here is that each input can only correspond to one output. Each x can only correspond to one y. Otherwise, we declare the function to be poorly defined. It's not defined. Not undefined, it's just poorly defined. So the restriction, or the limitation, each x can only correspond to one y. Or the other way around if we write x as a function of y. The limitation here is that each x can only correspond to one y. For most of the time, this is not really an issue. We have ways of getting around this if we need to. One example where this would not be a problem is we'll say that f of x equals x squared. No trouble here. Each x corresponds to one y. In a case of a parabola, we can write y as a function of x because each x will correspond to only one y. Each number has only one square. Where we run into an issue is something like a circle. Spelled X wrong. Where we run into an issue is when we have something like a circle. In this circle, there are some X that correspond to two different Y values. So here is a value of X that corresponds to two different Y values. Fortunately for our heroes, we can get around this depending on, as long as we're aware of what we're dealing with. We know that the equation for a circle is x squared plus y squared is equal to r squared. So we can write y as two functions of x, plus or minus the square root of r squared minus x squared. So we have a workaround where we write y as two different functions of x, the top semicircle and the bottom semicircle, with an overlap of the zeros on the x-axis. So this is a workaround, though. We represent the circle with two separate functions. But it's important to note that this is a workaround. We're saying we can't write one function that describes this circle. And once again, in this case, we are relying on a relationship between the variables. How are x and y related to each other? Our next way of describing curves in R2 is with an equation, and we could see one right here. In fact, the one that I'm going to use because it's always a circle. Also because we're going to parameterize the circle, and we already know a parameterization of the circle. It's super convenient. So another way we can describe a relationship, a curve in two-dimensional space is with an equation involving the two variables. Equation. We can write an equation involving the two variables. And our favorite example is going to be the circle. X squared plus y squared equals r squared. This is an equation involving x and y, and we know that this equation describes a circle with a radius of r centered at the origin. When we're using an equation, we're not limited to each input having only one output. We can't use our function trickery for when we're dealing with just an equation. We have to do something else like implicit differentiation, since this is a calculus class. But that removes that limitation of each input having one output because we don't have inputs and outputs. We just have a relationship between the two coordinates. So it eliminates the limitation. So we eliminate the limitation on input-outputs by eliminating the inputs and outputs. A little heavy-handed, but effective. We make an equation. So the nice thing is we can take these equations and we can write them as functions as long as we remember that we might not be able to write just one function, like with our circle example. We know that if we try to write y as a function of x, I'm going to need two functions, one for the top and one for the bottom. Also, if I try to write x as a function of y, I would need two functions, one for the right semicircle, one for the left semicircle. But as long as we're aware of what we're dealing with, we can generally work around that. And if we need functions, we could probably get functions. So the nice thing here is that if we need functions, we can get functions. But we will have to remember about any limitations that come up. The usual limitation that's going to come up at this point is that we're going to, if we have a square root, we're trying to invert something and we try to invert a square. A square is not an invertible function because the inverse of a square or any even power is that even root. The inverse of a square is a square root. The inverse of a fourth power is a fourth root. And even roots lead to this plus or minus business because even powers don't create one-to-one functions. Because even powers make negatives positive. So x, in the case of x squared, 2 squared is 4, but also negative 2 squared is 4. So if I say, where did this 4 come from? We don't know. We can't go back to where we started. Any questions? Comments? Snide them up. It's really weird to try to work with sleeves. Normally I don't have sleeves getting in the way. And these are like really inconvenient sleeves. I don't know how the Jedi do their friggin' dishes, man. This is like, this would just be soaked, right? Maybe they, yeah, maybe they just use the Force. Just like that. If you use the Force to wash dishes, are you going to drop more dishes or fewer? Like, are they going to be slippery in your hands is what I'm saying. Because like, if you have like slippery, soapy dishes, they're soapy dishes, they're slippery. But if you're using the Force, is that same slipperiness still in effect? I secretly know the answer. What's that? Yeah, it would be the Force, but does the Force have like fingers? I don't know, maybe they're just more grippy. Now it's kind of bugged me all day. Oh well, we got shit to do. So the common problem that we have with these two methods, as useful as they are, is that we're creating a relationship between the two variables. It's an expression about how x and y are related to each other. So that's where we start, where we want to get away from that, we start using parametric equations. The advantage with parametric equations, now I'm imagining Obi-Wan doing his dishes, like with the Force from the couch while he's watching TV, and all of a sudden dropping one because it was slippery. The advantage of using parametric equations is that the x and y are defined independently of each other and written as functions of some parameter that sits outside of the x and y coordinate system. So we skip the relationship between x and y, we define x and y independently of each other. We define x and y independent of each other, rather as some function, let's say as functions of some parameter and this parameter sits outside of the space, outside of x and y. It's not a coordinate, it's just some parameter. What I mean that by when I say it sits outside of the 2D space, it's not one of the coordinates. X and Y are locations. T is not a location, it's just a parameter. So this is our goal with parametric equations. Make x and y independent of each other and write them as some parameter. Write them as functions of some parameter that sits outside of the space. It's not one of the coordinates. We're just using it to draw x and y. And we'll use our favorite example of this. It's going to be a circle. So set your Wayback Machine to trigonometry. We're going to look at the unit circle. The coordinates on the unit circle, remember that the x-coordinate is the cosine, and the y-coordinate is the sine, and the parameter is the angle. So the location is based on the angle. So this is going to be cosine of t and sine of t. And that location is determined by the angle t. And this gives us all of our points going around the unit circle. So for various values of t, when t is 0, cosine of t is 1, and sine of t is 0. That corresponds to this point. We get 1, 0 when t is equal to 0. When t is equal to pi over 6, the x-coordinate is root 3 over 2. The y-coordinate is 1/2. I have to go sideways. And so we're at this point when t is equal to pi over 6. And we can just keep going around. When t is equal to pi over 4, we get root 2 over 2, and root 2 over 2. Pi over 3 or 60 degrees, we got 1/2, and root 3 over 2. And then at pi over 2, we're at 0, 1. One of the other things that we get when we define the circle this way, another thing that we get when we define the circle this way is that we get some direction on the circle. So if I set up a set of parametric equations where x of t is cosine of t and y of t is sine of t, the other thing that we want to tell our reader is what values of t we should use. So I'll say, let's do x is cosine of t and y is sine of t for t between 0 and 2 pi. Now, not only do we know that this makes a circle, but it's going to make a circle starting at 1, 0 and going around once counterclockwise. So there's more information with this parametric equations. So parametric equations also establish an orientation on our curve. So one other thing to note is that when we make a parametric set of, when we define a curve with parametric equations, we are also setting up an orientation because the values of the parameter have some smallest value and some largest value. So that sets up a direction. So this set of parametric equations will be a unit circle starting at 1, 0. Going around once counterclockwise. Oops. One thing to note is that this is not incompatible with stuff that we already know. We know the equation for a unit circle. The equation for a unit circle is x squared plus y squared is equal to 1 squared. And if x is cosine of t, and y is sine of t, then this is still true. Cosine of t squared, or cosine squared t, plus sine squared t is equal to 1. So it fits with our old description. Which is good. If it didn't fit with our old description, then we wouldn't be doing the same thing. And I wouldn't get to use this circle as such a good example. Any questions? Wearing the robe also makes me want to like close it and then like fold my arms, holding it closed like this. Or stand there like Obi-Wan from A New Hope. Like, put my hands up on the belt because the belt is sitting so high. Walking around with the hood on is not really useful because the hood is like not useful hood. It's kind of like designed to be a movie hood, and it comes down all the way over my friggin' eyes. So, not very practical. So what we're doing is we're defining x and y independent of each other as functions of some parameter t that is not a coordinate. The other way that we want to make sure that this is backwards compatible is that if we have a function, can we parameterize a function? The answer is no, we totally can't. So moving on, I'm just kidding. Obviously we can because I wrote parameterize a function and I put a big old box around it. The cheapest way to parameterize a function is to make the input a parameter. That's like the cheapest way to do it. So the cheapest thing to do is make the input the parameter. So for example, if we have a function where f of x equals x squared, that is the y coordinate is equal to x squared. Just make x of t just t. X is the parameter, and then the y coordinate is the function. If we do this for all values of t, then we will get the whole parabola. We can also sideways our parabola. If we have a sideways parabola, we'll just make the input the parameter. So in this case, x is a function of y. So y is going to be our parameter here. So x of t will be t squared. And we can make y of t the parameter. How's everybody okay? I wonder if you have Jedi mind trick. You ever accidentally drop that on your friend? Like friends are like, oh, hey, let's go get burgers. And you're like, well, I don't feel like burgers. And then your friend will be like, I don't feel like burgers. But can you accidentally just like toss it out there, or do you have to concentrate on it? And if you do have to concentrate on it, like if you like get older and start getting dementia, do you accidentally start throwing it around? I'm just wondering how much crossover there is with like X-Men and like Professor X when he starts to lose his mind, and like Jedi in the Star Wars universe. You know what I mean? Because the other thing too about Jedi that really kind of bothers me is they all have this like, oh, these aren't the droids you're looking for. And they all seem to be able to freaking do it. That's like messed up. Like if y'all are like, oh, I don't feel like doing my homework. You feel like doing your homework. I mean, I'm taking all of your agency away and just like forcing you to do something. That's pretty fucked up. I never used the Jedi mind trick on any of you that you know about because I make you forget. I'm just kidding. So one of the things that goes along with this particular parameterization is that we have established an orientation on our parabola. It's not just going to be this parabola. It is a sideways parabola, but it's not just going to be a parabola. It's hard to make these symmetric when you're doing them sideways. So not only because we've parameterized our parabola, we've not only just produced this parabola, but we've also given it an orientation. So this parabola has a direction. T goes from negative infinity to positive infinity. When t is negative infinity, that's when y is negative infinity. So I've got this from down to up orientation on our parabola. Parameterizing a function will give it some order or some orientation. So it's going from down to up. A parameterized curve will always give an orientation to the curve. But we have a lot of control over how this operates. We still have a lot of control over how this operates. Let's suppose that I want this same parabola, but I want the opposite orientation. Let's suppose that we want this same parabola, but we want the opposite orientation. I want it to go from top to bottom. I want it to appear that way. Forgot my rewritable notebook. See, sleeves. Suppose that we want the orientation to go from top to bottom. So x of t is still t squared. All we have to do is change t. Since t goes from negative infinity to positive infinity, if I just want to change the direction, just change the sign of the input. So make y of t negative t. And we'll still keep t going from negative infinity to positive infinity. But now the first thing that we're going to plug in, now remember, we get to say this because we're in calculus now. The first thing we're going to plug in is negative infinity. It gets multiplied by -1. And so our first thing we plug in is actually positive infinity. So that reverses the orientation. That produces a reflection about the x-axis in this case. Because of course it does. Changing the sign of the input produces a reflection about the output axis. That's always been the case ever since you learned about adjusting graphs in trig. Changing the sign of the input produces a reflection about the output axis. Changing the sign of the input will produce a reflection about the output axis. Think back to trig. If we look at y equals sine of theta, and I plug in negative theta, if I change the sign of the input, we're going to reflect about the output axis. When we change the inputs by multiplying by -1, I made all the negatives into the positives and all the positives into the negatives. I've just taken the x-axis, moved positive infinity to negative infinity to positive infinity. It reflects about the output axis because that's where nothing changes. When x is equal to 0, -1 times 0 is still 0. Any questions? Is everybody okay? And I go, yeah, it's cool. It's parametric. It's just simple. It's actually a useful way of thinking about how things are operating. Let's jump over into Desmos. Green, go away. There we go. Nope, that's not the one. Let's just get a new Desmos. So what we've done here is we've taken the basic graph in basic black, and instead of going from 0 here to infinity, I've changed the direction. Infinity, so instead of plugging in pi and going over here, we're plugging in negative pi, so it's going the other direction. We can do this with other changes to the input. If I do sine of 2x, the x-axis is going twice as fast. Where once we had pi is now 2 pi. That's why the graph has compressed. That's why the period got shorter, because the x-axis is going twice as fast. We can still see that the function is periodic because the x-axis is going twice as fast everywhere. So if we slow things down, now the period is twice as long at 4 pi because the x-axis is going half as fast. Instead of having an x-axis, we're looking at what's going to happen if we have a 0.5 x-axis. So we're moving along the x's twice as fast. Half as fast. But it's half as fast everywhere, and that's why we still have a periodic function. If I change how fast the x-axis is going everywhere, what we see happening here is that the x-axis is coming in faster the further along we go. We're getting from 0 to 2 pi. 2 pi is now at the square root of 2 pi. So one cycle goes from 0 to the square root of 2 pi. The next cycle goes from the square root of 2 pi to the square root of 4 pi. This is compressing down because we're taking infinity and we're moving it closer, or we're getting to infinity faster, but not evenly. That's why the function, I keep pointing down here like it's going to show up on the screen. But we're not doing this evenly. As x increases, we're going through the x's faster because we're going through an x squared. Also notice that I have created some vertical symmetry because now the negative x-axis looks exactly the same as the positive x-axis. That's why we see the symmetry, the same stuff on either side. Here, I've taken the x-axis and replaced infinity with the square root of infinity. So it's taking longer to get places. Also, all the negative stuff we can't deal with anymore. Although if I make the absolute value of x, then I've made the negative look just like the positive, and that's why we can get symmetry. How's everybody okay? Does everybody remember trig? It's tricky. It's tricky because it's a fall semester. And some of you might be right out of high school coming into fall semester and you had a pre-calculus class. And it might have been like my trigonometry experience. So I was in a class in high school called Algebra 2/trig. The /trig part was 3 weeks at the end of that year. So I had like 3 weeks total of trigonometry before they're like, all right, you're in pre-calculus now. It's like, oh, that trig seems kind of short. Because like I got some classmates over here, they're doing a whole semester of trig. And they're like, oh, you'll be fine. They're like, oh, we'll cover it in pre-calc, right? We'll get into pre-calc and we'll talk about all the trig that we missed. And we did not. And so I walked into calculus and she's like, all right, remember trigonometry? Is there a quiz on trigonometry? And she was like, oh, no. Then I'm like, oh, yes, I remember trigonometry. What specifically? In case I want to look it up later to help my friends who don't know anything. Then I had to go get a trig book because we didn't have the internet. Because it was in a land before time when dinosaurs ruled the earth. What are we talking about? Another famous one that we like to see, that we always like to draw, that we can draw now because we're in calculus and we understand stuff like this, is we have the sine of 1 over x. Now, all kinds of crazy stuff is going on, but look what happens when we look at 1 over x. Remember, we're not allowed to say 1 divided by infinity is 0, but if we think 1 divided by infinity is 0, by changing the input to 1 over x, I've taken 0 and moved it off to infinity, and I've put infinity way down here at 0. So normally, sine says, I need to get, I'm going to start at 0, and I'm going to do an infinite number of oscillations before I get while I go to infinity. But now infinity is this one point right here at 0. I've moved infinity to 0, and now I've got to cram in an infinite number of oscillations for sine as we get closer to 0. This clearly doesn't work, and if we zoom in, it's just like we're going down a hall. I'm afraid I can't do that, Dave. Has anybody even seen 2001? The Space Odyssey? So what we're looking at, even though we're looking very close, we're trying the grapher is trying to graph an infinite number of oscillations before we get to 0. And there's not enough space. That's why this looks like this big red wall. Any questions? Red's stressing everybody out. Let's make it orange to be more festive. Or green. Green for go. That's going to do it for today. We'll talk more about parameterizing functions and parametric equations. That's going to do it for today. I will see you all on Monday. Everybody have a good day. And thanks for playing. I've got a substitute coming in tomorrow to cover the classes. So, all right. Everybody have a good weekend.